Okay, elastic string of natural length, string not a spring, natural length 1.6 meters, as modulus or lambda is 120 newtons. One end is attached to a fixed point O, the other end particle is released from rest 2.1 meters below O, comes instantaneously to rest at B, which is vertically above O. So we've got O there, and spring going down to a particle P. It's released from rest, and that's position A. So that's A, but that's my particle. And let's get rid of that. Natural length is 1.6 meters, and it's pulled down a further to 0.5 meters. And I've got to verify the distance is 4 meters from A to B where it stops. Well, that's 2.1 meters, so B is going to be right up here. If it goes up there, then that's going to be above my 1.6 meters of natural length. So it's going to actually go up there. The whole thing up there is going to be 1.9 meters. And so it's going to be stretched up here by 0.3 meters. It doesn't actually have to tell me to find how far it goes up. It just says verify. It's saying here. So I use energy, and I'm going to do total initial energy, and I'm going to take this bit to be my baseline. And so I put my forces on here. I've got there, it's weight 1.5 newtons, so it's 1.5 newtons. So that's mg is 1.5, and I've got tension going up here, and tension, as we know, I've got lambda is lambda x over L, and lambda, it says, is 120. So total initial energy, and that's made up of elastic potential energy and gravitational potential energy and kinetic energy, and that's 0 and that's 0. So elastic potential energy, which is lambda x squared over 2L, so that will be lambda, which is 120, times by the extension, which is 0.5, and that will be extension squared over 2 times the natural length is 1.6, and that gives me 9.375. I need to work out total final energy, and this is going to be made up of my elastic potential energy, which is lambda x squared over 2L, and my gravitational potential energy, which is mgh, and 0 kinetic energy, because the kinetic energy, it says it's instantaneously at rest. So it's total final energy, elastic potential energy, lambda 120, times by my extension. Well, the whole thing goes 4 meters up, so this is 2.1, so that's 1.9, and so it's going to be a stretch and extension of 0.3 squared all over 2 times 1.6, that's 2L, plus my mgh. Now mg is 1.5 times by my h, which is 4 in this case, and that equals, if I work this out, that's 3.375 plus 6, which equals 9.375. Therefore AB is 4 meters, because the initial energy equals the final energy. That's good. Part 2. Maximum speed of P. What's well, find maximum speed of P during its upward motion from A to B. So I've got going down like this, and so I've got, that's my thing I look at. This is my initial length, 1.6 meters, and I say it's stretched down there by x, and that will give my x double dots. My acceleration is like so. Put my forces on there, 1.5 newtons, and T, which equals lambda x over L. And then I've got to think, when does this max speed happen? Max speed occurs when acceleration is 0. And acceleration is 0, so that actually will be the equilibrium position of simple harmonic motion. It will be when resultant force equals mass times acceleration. A is 0, so resultant force equals 0. Either, i.e., the upward force equals the downward force. And so that will say that lambda x over L must equal 1.5. And so that's 120 times by x over 1.6 equals 1.5. And that works out that x equals 0.02. And so that is the extension, which is a tiny bit down here. That is the extension I get when the acceleration is 0, and therefore it's at its maximum speed. And now I can do total initial energy equals total final. And the initial energy is just got elastic potential energy, and that's what I worked out to start off with, which is 9.375, and that equals a total final energy, which is elastic potential energy. So elastic potential energy is lambda 120 times by the extension squared, so it's 0.02 squared, all over 2L. That's 2 times 1.6. That's the elastic potential plus the GPE, which is that's plus 1.5. That's the mg, and he times it by the h, and the h has gone up by 0.48. And then finally I've got plus a half, and the m is 1.5 over 9.8, and that will be v squared, half mv squared. If I work this out, then I get v squared equals 9.375. Take away the elastic potential energy when it's stretched down by 2 centimeters, which is minus 0.015. And I've got to also take away this bit here, which is 0.72, and that's will be what v squared. Oh, but then I need to multiply by 19.6 and divide by 1.5. So that's all of that bit, and so that gives me v squared equals 10.6098 something, and was v equals that rather, because I have to square root it. That's what v squared equals. V equals 10.6, so v equals 10.6 to 3 significant figures. And that's question 5 done.